Hi guys, so this is the PowerPoint for March 23rd. This is our second week of online learning. If you haven't downloaded the notes yet, please do for Acids and Bases 2. You can go to Microsoft Word and edit them right into it. Just download your own copy of it, or you can print the PDF, or just get a notebook and follow along. Make sure you're taking notes so this way you can answer the homework that goes along with it. One thing that I do want to do, I know every Monday that I try and ask you what you're celebrating. So what's going on? Who are you celebrating? Anything that you guys have been doing, because obviously I haven't seen you. So I really would love to hear what you are celebrating. So just message me or text me on Remind and let me know. I'm going to celebrate everybody that has been keeping up the work and keeping in touch with me, because that is definitely not easy to do on your own. So I commend you guys for doing that for not only my class, but other classes. If you haven't gotten on and started the work, there is still time. Like I said in the remind message, you don't want to fall behind because you've put in 7 months of work so far. You don't want to fall behind at the very end here, okay? So make sure you stay in touch with me. Make sure you get on everything that you need to. If there's a reason that you can't, you have to message me so this way I can fix things for you and make sure that you do have access to everything that you need, okay? Tonight's homework is going to be CASEL Learning Assignment 323, and that's going to go along with what we're doing here. You're completing the chart on acids and bases too, and then there are questions underneath it, so you can do it on paper first and then go into CASEL Learning and submit it. So this way you can kind of practice with it if you need to write anything down. My office hours, and I'll go over whatever notes you need, are between 11 and 2:30, so I'll be logged in and I get notifications when you guys log into it. We can go over whatever questions that you have. Okay, if you're not on Microsoft Teams, I highly recommend it. And then the Remind codes are at the bottom here if you're not on Remind, or if you need to add your parents. Okay, so I want to go through acids and bases, just a little bit of a review. How do we tell the difference from acids and bases 1? So the chart that's underneath here, you guys can fill in. I put in table K and I put in table L because this is where you're going to find the most common ones here. So looking at acids first, something you should know is that they taste sour. You're not going to taste any of them from lab, but like lemons or soda, they have acid in them. They've got a little bit of a sour taste. So citrus fruit has citric acid in it. They have a pH less than 7. So we're going to talk more about that today, but I told you it can range anywhere from 0 up to 14. If it is less than a 7, then it's going to be categorized as an acid. The lower the number is, the stronger the acid is, and the closer that it gets to a 7, the weaker the acid is going to be. They're all electrolytes, and that was my trick from the last PowerPoint that we did. You want to think of ABS. So whenever you hear the word electrolytes, everybody always thinks, oh, you get that from Gatorade. Well, who's supposed to drink Gatorade? Athletes. And what type of body do they typically have? They have ABS on their stomachs there. So ABS are acids, bases, and salts. Anything that is an acid, a base, or a salt is categorized as an electrolyte. They can be weak or strong. From table K, which is what I have here, and that's from the reference table. And then the formula if you are an acid. So hydrogen with a non-metal. So for example, looking at table K, the first one, hydrochloric acid is a hydrogen bonded to a chlorine. There's the non-metal. A hydrogen with a polyatomic, so something from table E. If you look at nitrous acid here, it's a hydrogen and it's bonded to this polyatomic NO2. And then the last way that you can be an acid, the formula that you can have is where it ends in COOH. We call that an organic acid. Down here at the bottom of table K, you see it ends in COOH. That's going to be the formula for an organic acid. All right, talking about bases, they taste bitter. So if you've ever tasted something that's basic, it'll have kind of a bitter taste. It'll feel slippery, so kind of like soap. They have a pH above 7 on the scale, so anything 8, 9, 10, obviously going up to 14 is going to be a base. They're electrolytes. Again, ABS, acids, bases, and salts are all electrolytes. They can be strong or weak. You're going to find them in table L. It's on the same page as table K. And then their formula is going to be a metal with an OH. The only one that's a little bit strange here is going to be aqueous ammonia, NH3. But if you look at the first three that they gave you sodium combined with hydroxide from table E, because that's a polyatomic. Sodium is a metal, it's from group 1. If you look at potassium hydroxide, again, potassium is a metal. If you look at group 1, your periodic table, mostly made up of metals, but on the left side in group 1, you have metal, potassium, combined with hydroxide. And then calcium is a group 2 metal. So anytime you have a metal bonded to hydroxide, it's going to be a base. Okay, what you guys are going to do here is watch the video. It just kind of shows you, but you can really just look at the picture here. There's 4 different substances. So looking at row A, row B, row C, and row D, it's 3 samples of the same thing. So these 3 are the same, these 3 samples are the same, these 3 samples are the same, these 3 samples are the same. How would you identify, if I only showed you this picture, which one is an acid, a base, or a neutral substance? So how would you be able to tell? What could you physically do to potentially test for it? So think about what we've talked about in terms of acids, bases, and salts. At the end of the video, you guys are going to look at another video where we test them using some of the things that you guys learned today. Okay, so the pH scale, it's going to express the concentration of the hydrogen, or we call it a hydronium ion, from 0 to 14. So like I said, if you are 0, you're going to be a very strong acid. The further that you get towards the middle, towards 7, which is a neutral substance, the less acidic you are. As you go from 7 up to 14, you're going to become more and more basic. It's going to become a stronger base once it gets up to 14. The pH scale is going to be logarithmic. So one move on the pH scale represents a 10-fold change. So think of this, the Richter scale, I believe, that you guys did in earth science moves the same way. Going from one number to the next, it's 10 times the amount. So for example, a solution with a pH of 3 has 10 times the amount of hydrogen than a solution with a pH of 4. Okay, so as you move down from a 4 to a 3, it's 10 times more acidic. Okay, if you move from a solution that has a pH of 4, so going from a 3 to a 4, it's going to be 10 times. If you go from that 3 up to 5, it's 100 times the amount of the solution. Okay, so 5 down to 4 down to 3 is 100 times more acidic. Okay, and it's going to keep moving at that 10-fold rate. So looking at the example number 1, just how would you read this scale from 0 to 14? I'm starting with a pH of 1, and I want to know how many times the amount of hydrogen is going to be compared to the solution with a pH of 6. So how are we going to look at this? Find number 1, move it to 6. I look at the scale, I see that 1 is down here, and I want to get to a 6. So as I go from a 1 to a 2, we know that that's going to be 10 times the amount. If we keep going, that's another 10 times. So going from a 1 to a 3 is now 100 times. If I go from a 1 to a 4, that's going to be 1,000 times greater. So jumping from 1 all the way up to a 4 is 1,000 times. Going from a 1 to a 5 is 10,000 times. So in order to figure out going from 1 to a 6, you're just going to add another 0 on the end. It's 100,000 times. The concentration is 100,000 times different. So in terms of hydrogen, so going to be an acid, acids have the H plus on them, and we know that bases have the OH minus on them. So going from a 6 down to a 1, it's 100,000 times more acidic. If I had a pH of 6 in my solution, going down to a 1, it's 100,000 times. Looking at the next one, a solution with a pH of 2 has how many times the amount of hydrogen ions or hydronium ions compared to a solution with a pH of 5. You're going to do the same thing. So find each one of those pieces going from a 2 to a 5. I now have to move from each level up. So starting from the first one, a 2 to a 3, it's going to be 10 times. From a 2 to a 4, it's 100 times. From a 2 to a 5, it's going to be 1,000 times. Okay, so it's the same concept here. 10 times stronger. Moving to the next level is another 10 times stronger. Moving to the next level is another 10 times stronger. Okay, it moves at a 10-fold change. As the H plus, as the hydronium ion or the hydrogen ion concentration increases, that's what these brackets mean, concentration, the OH minus is going to decrease by the same rate. So essentially, if you are getting more acidic, you are getting less basic, okay? If you are getting less acidic, so if your hydrogen ion concentration is decreasing, you're going to be getting more basic. The OH minus concentration is going to be going up. So if the pH changes from a 3 to a 4, from a 4 to a 3, the hydrogen increases by 10 and the OH decreases by 10. For example, number 4 here, the pH changes from a 6 to a 2, so 6, 5, 4, 3, 2. We're going from a more basic to a more acidic environment because, again, acids are going to be less than 7. So going down, you're getting more acidic. The hydrogen ion increases about 1 times 10 to the 4th, or it increases about 10, decreases about 10,000 times for OH. These are the same exact amounts, okay? Increasing by a certain amount to become more acidic, it is decreasing in that same amount that it was basic. If the pH changes from an 8 to a 13, the hydrogen ion we know is going to decrease because we know going up, you're getting more basic. So your hydrogen ion, which was making it acidic, is going to decrease about 1 times 10 to the 5th times, which means that it's going to increase about 100,000 times. Same exact amount here. You can write it in scientific notation. You can write the whole number out. The more acidic a solution is, the more hydrogen ions, or the more hydronium ions. The more basic a solution is, the more hydroxide ions it's going to have. Okay, H plus goes along with an acid, OH minus goes along with your base. If an acidic solution is added to a basic solution, the pH is going to decrease. Why does that happen? Because acids have lower than 7. So if I'm adding more acid to a solution, the pH is going to go down. If I have a basic solution and I add it to the acidic solution, the pH is going to go up. Why? Because bases have pHs that are higher than a 7. So by adding more base to it, it's going to make the numbers go up. Okay, looking at indicators, those we talked about briefly the other day, but this is going to focus more on table M. Substances that change color when they're exposed to acids or bases. So they indicate whether the solution is acidic or basic or what range it's going to fall into. They change color by gaining or losing a proton, which we call H+. Okay, a proton looks just like a hydrogen ion here, or a hydronium ion. The table is going to give 2 color spectrums. So it's going to go from one side to the next side, depending on the range that it falls into. The other thing that you can use to test is called litmus paper. I'm going to show you at the end when you look at the video. You can use litmus paper to test whether your solution is acidic. So if I take a piece of litmus paper and it turns red, it means that it's an acid. If I take a piece of litmus paper and I put it into the solution and it changes to a blue color, it means that it's a base. It doesn't tell me the pH range, it just tells me whether the solution is acidic or basic, and that's it. It doesn't tell me the actual pH, or doesn't give me an idea of where that pH range is. Using something from table M, you can actually look at each one of these indicators. So methyl orange, bromothymol blue, phenolphthalein, litmus, like litmus paper, bromocresol green, and thymol blue. These are all different indicators that you can use. Okay, these are the approximate ranges when they are going to change. So anything below the number is going to fall into the first color. So the first one would be red. Something 3.1 or below is going to come out red when I put the drops into it. If I have methyl orange and I put it into a solution and it changes to yellow, it means that it is above a 4.4. Okay, so this is how these changes work. Looking at the question here, what is the color of bromocresol green? Okay, so I know that I have to be looking at this particular indicator. What is this color going to be in a solution that has a pH of 2? So, looking at bromocresol green, I see that the pH range is 3.8 to 5.4. It's going to change from a yellow to a blue color. Because 2.0 is below 3.8, what color does that mean it's going to be? It's going to have to be a yellow color. So if I were to take this indicator and I were to put a couple of drops into my solution, I'd be able to tell that it is a number below 3.8. It's going to come out yellow. Okay, couple more questions just to practice. In a laboratory investigation, I've got HCl solution with a pH value of 2. It's used to determine the molarity of a KOH solution. So HCl, you guys should be looking at that. Okay, is that an acid or a base? I see that it's a hydrogen attached to a nonmetal. That's going to be an acid. I see KOH, that's a metal combined with a hydroxide ion. That means it's going to be a base. So I've got an acid and I've got a base here. A 7.5 milliliter sample of the KOH, the base, is exactly neutralized by 15 milliliters of the acid, which is HCl. During this activity, appropriate safety equipment is used and safety procedures are followed. So this is just the background on it a little bit. Looking at the question on the left first, determine the pH values of a solution that is 10 times less acidic than the HCl. Okay, determine the pH. I'm looking for something that's 10 times less acidic than the HCl. So I have to find HCl in here. If I take a look, I see that the HCl has a pH value of a 2. Now, I know that acids are going to have pHs that are lower than 7. I know that bases are going to have pHs that are higher than 7. So if I'm getting less acidic, what's going to happen? Should the number be going up or down? The number should be going down if it's getting more acidic. If it's getting less acidic, it means that the number should be going up. Now, if the solution is 10 times, we talked about this in the last slide, if you're doing anything that's 10 times the amount, it means that you are going up by 1. So originally our sample had a pH value of 2. If it's getting less acidic by 10 times, which means it's getting more basic, it should be going from a 2 up to a 3. So our final pH should be a 3. Again, if the solution is 10 times less acidic, it means that it is 10 times more basic. So it's getting further towards the base side, so closer to the number 14. Everything goes up by 10 times as you move from number to number. So only 10 times would be a pH of 3. If the question said 100 times less acidic, it would make it go from a 2 to a 4. Okay, state the color of the indicator, bromocresol green, if it is added to a sample of the KOH. So we know that KOH is a base. We know that we're using bromocresol green, so I'm going to find it on the list, the same one we did in the last slide. Because I know KOH is a base, it's got a metal ion combined with a hydroxide ion. I know that it's going to be this base, and if I know bases, I know that they have pHs above the number 7. So anything above a 7, according to bromocresol green, is going to be a blue color because it's above 5.4. Bases are above a 7. It's going to be a blue color if I were to put a couple drops of that indicator in. Okay, again, looking at the pH scale, state the color of methyl orange indicator after the indicator is placed in a solution of 0.10 molar ammonia. So methyl orange, I'm going to find on my indicator list, and I see that methyl orange is the first one here. It's got a pH range of 3.1 to 4.4, and it'll change from a red to a yellow. I see that I have ammonia, so we're going to look more at molarity in the next couple lessons, but I see that I have ammonia. And what do we know about ammonia? We know that ammonia is going to be from table L. So table L shows me bases. I know that ammonia is a base. What do we know about bases and the pH scale? We know that acids have a pH lower than 7. We know that bases have a pH above a 7. So looking at methyl orange, I can see here that the base color is going to be yellow because anything above a 4.4 would change it to yellow. Because all bases are going to have that pH above a 7, I know that it would change to yellow. Okay, so again, looking at the pH scale, 1 liter solution has a pH of 7, and a 1 liter solution has a pH of 5. So looking at our scale here, we're going from 5 to 7. I want to compare the two. Going from 5 to 6 is going to be 10 times stronger. Going from 6 to 7 is going to be another 10 times. Okay, so a couple things that we need to note here. Hydronium ions are H3O+. It's just what happens is the hydrogen ion bonds to the water, and it's going to add that extra hydrogen on it. But it's the same thing. A hydronium ion is the same way as saying it's an H+. Okay, these are pretty much used interchangeably when we talk about acids. Hydroxide ion, you should see the word hydroxide, and you should know what the hydroxide ion is. Check table E. It's going to look like an OH-. So knowing that, I'm comparing the solution with a pH to a pH of 5. So tell me about the pH of 5. If I'm going from a 5 to a 7, there are two answers that you should look at and say, okay, I can probably get rid of these two. That's going to be choice number 1 and choice number 3, because 10 times would be just changing by one number, right? As we go from one number to the next, that's 10 times. I know that this is moving 2 spaces, okay? So from a 7 down to a 5 is going to change it, okay? The pH of 5 contains what? Does it contain more hydroxide? Does it contain more hydronium? So compared to a 1 liter solution with a pH of 7, a 1 liter solution with a pH of 5 is going to contain 100 times more of the hydronium ions. The pH of 5 is more acidic, so it's going to have 100 times more of that hydrogen ion comparing it, okay? If it was more basic, it would have more hydroxide, right? Because bases have OH, acids have the H+. Okay, again, couple things to note. Acids turn litmus paper red. So acid ends in a D, red ends in a D. Anytime something is turning red in litmus paper, it is acidic. Bases turn litmus blue. Okay, so if I have a piece of litmus paper and I put it into my solution and it turns blue or it stays blue, it is a basic solution. So what color, and down here I have a picture of the litmus paper that I'm going to test and you'll see it in the video, but this is essentially what they look like. So if I took a piece of red litmus paper and I put it in a solution and it stayed red, it means that it is acidic. If I took a piece of red litmus and I put it in a solution and it turned blue, it means that it is a base. Okay, and the same thing will go for that blue litmus. So what color will red litmus turn when I place it in a base solution? So anytime we have a base, it should turn blue. And this is specific for litmus paper. What color will blue litmus turn when you place it in a base solution? Again, anytime we have a base and we put any color litmus paper in it, it's going to turn blue. What color will red litmus turn? So I'm now working with red when I put it in an acid. Well, anytime you have an acid and you use litmus paper, it's going to turn red. And then what color will blue litmus turn when you place it in an acid solution? So I know it's an acid. Anytime we put either color in, an acid will turn it red. Okay, so using table M, you can also predict color changes based on the type of solution. So what color will phenolphthalein be in a base? So phenolphthalein is an indicator. We have it here on table M. I know that I'm putting it in a base. What do we know about bases? We know that they have pHs above the number 7. So because the range is between 8 and 9, let's say that it's a stronger base. It could be colorless to pink, but typically anything higher or a stronger base, it's going to be pink. It could be colorless if it was a weak base, something like an 8, but typically most of the bases are going to be pink. All right, what color will phenolphthalein, so same indicator, what will that be in an acid? We know that acids have pHs that are lower than 7, so anything below 7 for phenolphthalein is going to be colorless. All right, looking at a different indicator, we're working with bromocresol green. So I find bromocresol green from my table M. What color will that indicator be with a pH of 2.2? So going to the choices here, going to the pH range, I've got 3.8. Anything below 3.8 is going to be yellow. Anything above 5.4 is going to be blue. Anything in between this range is going to be green, right? Because in between yellow and blue, if you were to mix them, it would be green. So if I have a pH of 2.2, I know it's going to be yellow because that's below 3.8. What color is bromocresol green going to be in a base with a pH of 10? So anything above that 5.4 is going to be blue. So because my pH is above 5.4, it's a 10.0, it's going to be blue. Okay, so this is the chart that you are going to complete from Castle Learning, but my suggestion is to go through and answer it first on paper if you can, just so this way you can check it for each one of these different ones. I'm going to do the first one with you. So a pH of 2 is going to be what? So we know acids, bases, and if something is neutral, we know if it's neutral, it's 7. If it's below 7, it's an acid. If it's above 7, it's a base. So if I have a pH of 2, I know it's an acid. In phenolphthalein, so phenolphthalein is an indicator. You're going to look at table M. The range on it is 8 to 9. So between an 8 and a 9 is when it will change colors, so it'll indicate what's happening. Phenolphthalein, you'll see it goes from colorless to pink, so anything below an 8 is going to be colorless. Our pH is a 2. This one's going to be colorless. So I know that I have an acid because it is a pH of 2. It's very low. So if I were to put it in blue litmus paper, litmus is going to change colors. So the pH of 2, what color will it be on the blue litmus? It'll be red. Acids change to red. And then for my red litmus, if it's an acid, it's going to also be red. It's going to stay that color. So you guys are going to fill out this whole chart. It's on the Castle Learning assignment, so you can do it there. My suggestion is to do it in the chart here first. And then the last thing you are going to do is you're going to watch this video here. It's the same thing, but now I'm actually going to test it using different chemical properties. So what are some different chemical properties that we just talked about today that you could use to figure out which one is an acid, which one is a base, without touching them or without tasting them? So what else could you do based on what we talked about today? I go through it in the video here, so you can watch it on the slide, or you can, there's the video link that I'll put in that'll open up to the OneDrive account, so this way you can watch the videos and look at a couple pictures of it. Okay, so when you are ready, you can complete the Castle Learning assignment. If you have any questions, guys, please reach out through Remind or email so we can make sure that you guys are all on the same page.